So now let's focus on what's really happening inside those wires. So we know why they're moving. It's because the electrons are moving because of that potential difference that's applied. It gives them energy, almost like gravitational potential energy, except it's called electrical potential energy that gets converted to kinetic. So I have a question for you. I have a picture of a simple circuit. I have a battery here, I have a switch, and I have a little light bulb. And the switch has been closed, so you can see that the light bulb is on. And it says, how long do you think it takes an electron to reach the light bulb from the light switch once you turn the switch on? So the question I'm really asking is, how fast do you think those electrons are moving throughout that circuit? Are they zipping around at close to the speed of light? That light switch certainly gets that light to go on very, very quickly. Or does it take longer? So just give a guess. How long do you think that's going to take? So here is the basic answer to that question. It takes 68 minutes for an electron to move 1 meter. So certainly in this picture, that is not a meter apart. But if it was just 1 meter apart, just this big, or this big for a meter, if it was just 1 meter apart, it would take 68 minutes, longer than this hour, longer than this class period, in order for that electron to make it from one place to another. So a couple questions that brings up. One is, why are they moving so slowly? And another one is, well, then why does the light turn on so quickly if the electrons are moving so slowly? So the electrons are moving, if you divide that out, at about 0.000246 meters per second. That's incredibly, incredibly slow. But the lights, when we flip the light switch, the lights come on instantly. We aren't waiting around for those electrons to move. And so the important thing to remember when we draw this circuit, so we would have the battery here, we have the light bulb, we have the switch, which would be like this if it's open, and then when we close it, it's like this. So just showing you some of the diagram symbols that we'll use. Again, this is the positive and negative side of the battery. When we close that switch, what happens is the potential difference is applied to the circuit. We have to have both ends of the circuit connected in order for that potential difference to exist. You have to have the positive side connected to the negative side. And what happens is the electrons start moving because of that potential difference. But the key thing to remember is the battery is not a source of electrons. The battery is not just a whole bunch of electrons that, oh, now we have the electrons, so now we can have a circuit. The electrons are already in the wire from the very beginning. It's a conductor. It's filled with electrons, and some of those electrons are free to move. So what happens when you close the switch is it's a signal from that potential difference for all of these electrons to start moving. Think about a bunch of people standing in a line. These electrons are in this giant line. And when the switch is closed, the potential difference comes into play. It's almost like somebody yells, go, to that line of electrons. They all get the signal to move at the same time. So it's not like this one has to come out of the battery and make it all the way to the light bulb. It's just the ones that are already in the light bulb and in the wire right there that need to move through in order to start getting that bulb to turn on. So the next question is, okay, I know why the light bulb comes on so fast, because the electrons are already there. And as soon as I flip the light switch, boom, they're going to start moving. But now the question is, why are they going so slow in the first place? And in reality, the electrons are actually moving fairly quickly from place to place. But we need to realize that it's more like a pinball machine for those electrons. It's not like a nice clear hallway that you might walk down. It's like, again, more like a pinball machine. So imagine we're inside this wire, and inside this wire are protons, and protons are a lot bigger than electrons, right? And those protons are stuck right where they are. In fact, it's not just single protons, but it's actually groups of protons, right? There's atoms throughout this entire thing. And these little electrons get this signal all the way throughout, this signal that says go, and I got to go in a certain direction. So these electrons start moving. They have this energy to start moving now. But what happens is, as they're kind of zipping along, they run into things. So then they bounce backwards, and then they'll hit another proton, and then they'll bounce forwards, and then they'll bounce backwards again, and they'll bounce here. But they know they're supposed to be going this way, the energy is forcing them to go that way, that they'll hit something which will knock them backwards. So in between these collisions, the electrons are actually moving relatively quickly, but their net speed forward, if I just track the forward progress of the electron, that is very, very slow. And this forward speed, the net forward speed, is called the drift velocity. And the drift velocity is very slow in comparison to the actual speed that the electrons are zipping around with. So again, think about that pinball machine. It's going to take a lot longer for that pinball to make it from one place to another because of those collisions.